Here's the next problem. So a heavy rope 40 feet long weighs 0.7 pounds per foot and hangs over the edge of a building 110 feet high. So we want to know two different things: how much work is done in pulling the rope to the top of the building, and B, how much work is done in pulling half of the rope to the top of the building. Okay, so this is very similar to the bucket problem, but in this case, there's a couple things that we're doing a little bit differently. So let's start off with part A. Um, so let's say this is my building right here. Okay. And this building, how far? It's 110 feet high. Okay. So this thing is 110 feet high. And then you have some sort of rope dangling here. So you have this rope. Okay, let's just say that you have this rope, and this rope is 40 feet high. So figure is not drawn to scale because it looks like it's half of it. But let's say this thing is just 40 feet high. Okay, or 40 feet long. And we have other things in there too, that it weighs 0.7 feet pound per foot. Okay, so notice that there's only one thing that we're really doing, and that we're just carrying this entire rope. Now, if you think about this rope, if you were to start off pulling this rope up to the top of the building, it's going to be much heavier in the very beginning. As you keep pulling, then it's going to get a lot easier, and that's mainly because you're taking away all of this added weight from the very beginning. So and we can also see that the work is not going to be constant, because it does get easier when more of the rope is already at the top. So what I'm going to do is that I'm going to break this up, take a little slice of this rope, and I'm going to call it delta x, similar to what we've been doing. Okay, so I'm going to call this delta x. Whoops. So that little slice is just delta x. So the first thing that we want to figure out is how much force is needed to pull this amount to the top. Okay, and let me set up my axes. So let's say here is my 0, and then as I keep going down to this particular thing, I'm going to call this xi. So you might notice that wherever I place my 0, going either downward or upward, that's where I've been placing my xi. Okay, so what we want to do first is let's go ahead and find the force. So let's look at what type of units they gave us. So they gave us feet, and they gave us pounds. So they gave us US customary system. So basically this thing, the force is already there. We don't have to multiply it by 9.8. So let's look at the force of the rope. So here's the rope. The force, or the weight in this case, is going to be 0.7 pound per foot. But we do not want feet. So how far am I lifting this one to the top? Well, I'm lifting it xi units. Okay, xi feet. Again, you can also have said 40 minus xi. Still would have given you the same thing. So the feet are going to cancel out, and I'm going to get 0.7 xi. So that's going to be the force required. Okay, for me to lift up this little small thing. So basically, if this is a height of delta x, if I'm moving this little strip delta x units, then that means that my work is going to be equal to, if I wanted to make it like as a Riemann sum, is going to be the limit as n goes to infinity of the sum from I goes from 1 to n of the force, which is 0.7 xi, times the distance, which in this case is going to be delta x. Okay, so this is kind of like the more generic thing that you basically are doing. You don't necessarily have to write it down, but you know that the limit of a summation is just going to turn into the integral, okay, from a to b of this 0.7. This xi turns into an x, this delta x turns into a dx. Okay, so that's basically what the integral should be. Now, what would be the limits of integration? Well, they will be, since I'm lifting for part A, the whole thing is going to be from 0 to 40, okay, of 0.7 x dx. Okay, so now let's go ahead and take the antiderivative. 0.7 x squared over 2 from 0 to 40. It's going to give me 0.7 times 40 squared divided by 2, and that's going to give me 560 feet times pound. Okay, so that's the work required to lift up that entire rope. Okay, now now let's do part B. And part B might be a little misleading because you might think, okay, well, if it takes me 560 feet times pound to take the whole rope up, then it must take half the amount of work to lift half of it. Well, not necessarily, because if you were to say take turns with your friends, you pull up half of the rope first, and then he or she pulls up half of the rope next. Well, you would think that the second person is probably gonna use less work because the first person already did the most amount of work, because you kind of have this dead weight at the end. So actually, that's not very true. It's not gonna be half of the work. Okay, so for this next problem, how much work is done to pull half of it? Well, let's see exactly what's going on. So I still have the same scenario. Let me just draw my rope again. So here's my rope. Okay, looks kind of weird. Okay, so I'm still taking half of it. So let me just say I have half of my rope. Okay, I'm gonna call this the top half, and I'm gonna call this the bottom half. Now you're wondering, why are you breaking it up like that? Well, the thing is this is exactly what we are doing. We're doing two things. We are pulling half the rope up. So half of this rope, this top part, I'm going to pull it all the way up. Okay? So this guy, this whole thing, I'm pulling it all the way up, and that's what I want. But something else is occurring. You are also pulling the bottom half to where the top half is. So in addition to just moving this guy up, you're also moving this bottom part, let me put it in a different color, into the position of where this guy was. So you're doing two different types of work. You're pulling this amount, X amount of units, but you're also moving this amount to where exactly this top part is. So you're going to break it up into two different integrals. So let's first start off with the top part. So let's find the force due to the top part. Well, that's really easy because we've already done that. We already took a small little piece, called it delta x. What was that? That's going to be just this 0.7x. Okay, so the force at the top is just going to be 0.7 xi. So we've already done that. That was just something that we did in the part A. The only thing that's going to be different now is that you're not doing it from 0 to 40 anymore because we only want half of it. You're doing it from 0 to 20. Okay, you're not pulling the whole thing up. Okay, now what we got to figure out now is how much work is required to pull the bottom half to where the top part is. Okay, well, same thing as we did before. Okay, so how much does this cable or this rope, if I were to have delta x, how much does it weigh? Well, if we go back to the problem, it weighs 0.7. Okay, that's 0.7. What was it? Pounds per feet. I almost forgot. Okay, so this is the mass. Okay, not the mass. That is the weight. This is the weight, and I'm gonna multiply it by how many units am I lifting this guy all the way to the top? Well, I'm just lifting it 20 units, right? Because I'm doing it from 0 all the way to 20. So I'm moving this guy 20 units, 20 feet, 20 feet. Okay, so the feet are gonna cancel out, and what I'm left with is just 14 pounds. Okay, so I'm basically lifting this dead weight. So this, in order to move this guy up to where the first position is, it's just going to be 14 pounds. Okay, that's basically all it is. I'm moving it 20 units up. That's just because that's all I'm doing. I'm not lifting it all the way to the top. Okay, so we have this kind of, like, imagine this is just dead weight. Okay, so now my work is basically the sum of these two guys. So if I were to write it in limit form, limit as n goes to infinity of the sum from I goes from 1 to n, it will be the first part, the top part, plus the bottom part. Okay, now again, you don't need to write it this way. you can just write it immediately. The integral from what to what? From 0 to 20 of what? Of 0.7x plus 14 dx. Okay, now let's take the antiderivative. 0.7x squared divided by 2 plus 14x from 0 to 20. Okay, then we're just going to say I have 0.7 20 squared divided by 2 plus 14 times 20, and this gives me 420 feet times pound. Okay, so that is the work that's done by putting half of it to the top. Now, there is a rule of thumb in case you want to check your work. Usually when you want to have half of a rope, the work required for half of the rope to be to the top is usually 3/4 of what the original is. So if initially this 560 is how the amount of work that it takes for you to bring the whole thing up. And if I were to take 560 and multiply that by 3/4, that's going to give me 420, which is basically the amount of work that's required to lift it up only half. So this is kind of like a rule of thumb. That's usually what it is. So if you ever want to just check your work, this is basically what it is. But usually on an exam or a quiz, you might want to do this entire format.